Hey there. So today we're going to tackle ethers. But let's forget the dusty old textbook approach, okay? I want you to think of an ether as this special kind of molecular bridge. And in this explainer, we're basically going on a problem-solving journey. We're going to figure out not just what this bridge is, but how to masterfully build it, and, maybe more importantly, how to strategically break it. All right, so before we can even think about building or breaking this thing, we need a clear blueprint. Let's start with the absolute basics. What is an ether, really, when you look at its structure? At its core, it's actually incredibly simple. An ether is just an oxygen atom that connects two carbon-based groups. We usually just label them as R. So this ROR structure is the classic oxygen bridge that defines the whole family of ethers. It's elegant, it's simple, and it's the foundation for everything we're about to talk about. So yeah, that leads us right to the two big puzzles of ether chemistry. These are the questions that are going to guide our whole journey today. How do we actually construct this oxygen bridge? And then once it's built, how in the world do we take it apart? Let's start with that first challenge, synthesis. See, building an ether isn't always as straightforward as it looks. It's a process where the tiniest details can be the difference between getting the exact molecule you want and, well, a complete failure. So take this first method, for example, dehydrating an alcohol, like ethanol. This is a perfect example of a chemical tightrope walk. At 140 degrees Celsius, everything's great. Two ethanol molecules combine, and you successfully form your ether through a substitution reaction. But just crank up that heat to 170 degrees, and the whole reaction changes. It favors elimination, and you get an alkene you didn't even want. It's a classic temperature trap. That kind of fussiness about temperature is not great. It's not ideal for a reliable process. We need something more robust, something that's less of a tightrope walk and more of a solid, dependable construction plan. And that brings us to the hero of ether synthesis, the Williamson reaction. The Williamson synthesis is just beautiful in how efficient it is. You take an alkyl halide, you react it with a sodium alkoxide, and just like you see here, the alkoxide does this clean little backside attack on the alkyl halide, kicks out the halide, and bam, you formed that ROR bridge you wanted. It's a textbook SN2 reaction, and it works like a charm. So it seems like the perfect solution, right? A reliable tool for pretty much any situation. But even the best tools have their rules. And the Williamson synthesis has one critical constraint that you absolutely, positively have to know to avoid disaster. And here it is. This is the critical piece. The alkyl halide has to be primary. If you try to use a big, bulky tertiary halide like this one, the reaction just fails. So why is that? Well, the alkoxide is just too physically blocked to do that backside attack needed for substitution. It's like trying to park a truck in a bike lane. So instead, it just acts as a base, rips off a proton, and you get elimination, forming an alkene, the exact opposite of what you were trying to do. Okay, so we've pretty much mastered how to reliably build our oxygen bridge. Now it's time to tackle that second puzzle. Once it's built, how do we strategically take it apart? So ethers are famously sturdy molecules. They're pretty unreactive. They don't react with bases or most common chemicals. But they do have an Achilles heel, a really strong acid, like hydroiodic acid, or HI. This stuff can actually cleave that strong carbon-oxygen bond. But this raises the ultimate puzzle of ether reactions. When that bridge breaks, which side gets the iodine? Answering that question can feel tricky, but it's really not. We just have to think like detectives. We're about to uncover 3 simple clues that when we put them together will let us crack the code and solve any ether cleavage problem. Okay, our first clue is all about size. When both groups attached to the oxygen are primary, the reaction is a classic SN2 attack. So the iodide ion, it just goes for the easiest target, the smaller, less crowded group. The rule is simple: the little guy gets the iodine. Now, what's really fascinating is how the entire game changes when you've got a bulky tertiary group involved. Here, the whole mechanism flips from SN2 to SN1. The driving force isn't size anymore, it's all about stability. The bond breaks first to form the most stable carbocation possible, which is the tertiary one. Then the iodide just attacks that stable positive charge. So the rule shifts. The most stable group gets the iodine. And for our last clue, we're going to look at aryl ethers, like this one. That bond between the oxygen and the benzene ring, well, it's no ordinary single bond. Because a resonance, it has partial double bond character, which makes it incredibly strong and stable. It's basically unbreakable in these conditions. So the cleavage always happens on the other side, breaking that weaker alkyl-oxygen bond. So, we've gathered our clues. We've got the size rule, the stability rule, and the unbreakable bond rule. Now, let's put them all together into one single powerful tool. Think of it as the master key that can solve any ether cleavage problem you'll ever run into. And here it is. This is your decision tree. It's just a simple logical flowchart. You start with your ether and you ask the first question, is the oxygen attached to a benzene ring? If the answer is yes, you know exactly where that bond's going to break. If no, you go to the next question. Is there a tertiary alkyl group? If yes, you know the reaction is SN1 and the stable group gets the iodine. And if the answer to that is no, well, then you know it's an SN2 reaction and the smaller group gets the iodine. See? It's foolproof. And just like that, our journey's complete. We started with a simple molecular bridge. We learned the traps of trying to build it, and then we found the reliable Williamson synthesis. Then we put on our detective hats and uncovered the rules to systematically break it. We've totally cracked the code. You now have the master key, that decision tree that turns what looks like a complex puzzle into just a series of simple questions. So really, the only question left is this. With this new problem-solving framework in your toolkit,